Hello everyone, welcome on in. My name is Penn Center. We're here for lesson number 5 of the Friedberg reading group. So today we're going to be joined by Gumboy again. We're going to be talking a little bit about operations of linear transformations. So we're going to be looking specifically at composition and inverses, if I remember correctly, the 2 sections of the textbook. Hi Cold, hi Martin. First moment, yeah, you made it in. So that's what's on the docket for today. We're going to go ahead and just run through our pre-roll ads so that folks that are going to be joining us via Twitch don't get stuck by a pre-roll ad during the presentation. So we will take a quick little 3-minute break to run those ads and we'll be right back. Hi, Larson. Welcome on in. All right, I'll see you in a couple minutes, chat.
Time for a pop quiz. Easy as pie.
There you go, Cold. Looks like Enigma bot's down again, so I'll give you the QED that you so rightfully deserve. You have a couple more minutes to spam any memes that you want. Spam all of the emotes. There's like 2 minutes left. Oh, for the animation? That would have been really cool. Okay, is mine? Okay, well that's off. That's good. Larson, we're going to be talking a little bit about linear transformations. So this is part of our reading group that we're running through the Simple server. So we're going to be talking about composition and inverses of linear transformations. And Anders, thanks very much for the help this morning on that question. I woke up this morning and I'm like, oh man, I should be able to do this question, but I was struggling to figure out what was going on between S1 and S3. That was tricky. Very tricky. Well, it wasn't tricky once you pointed out what to do, but on Zero Coffee it was quite tricky. Alright, we're about 1 minute out. I know. Well, hopefully we'll be on a little bit later today as well. I should be on a little bit later when you wake up, I think. So if you need to sleep, go to sleep. But feel free to lurk if you want. What even is sleep? True. Goodbye, Larson. Who needs sleep? Okay, we're about 20 seconds out. I'm gonna go ahead. Let's remove this. And we're going to go ahead and mute our music. And we're going to get ready to get this show on the road. I also do have to close StreamerBot, so no more special effects, anyone, sorry. I'd already answered everything when I arrived. Well, I mean, you know, MathStack Exchange is helpful for things like that. Okay, we're going to bounce over into Discord. Hello, everybody, and welcome into, I believe this is lesson number 5. We have Gumboy back. Continuing on with where we left off before the holiday break, we're going to be talking a little bit more about linear transformations, and specifically thinking about kind of how to deal with composition of linear transformations and how to think about invertibility, if that's possible. So I'm going to go ahead and pass the floor off to Gumboy, and you are ready to go when you're ready, man. Let's see. Audio on my side doesn't look like it's porting through properly. Twitch, yeah. Let's see. That's probably in here. I probably shouldn't show that to the world. It was working fine last night. This is what happens when you go do like a reset of everything. So let's see. Output device needs to go to here. Right? So you can hear me, right, Gumboy?
I can hear you perfectly, yeah.
Okay, perfect. I think that might have fixed the problem. If you can go ahead and do a little intro, we can just check and make sure that things are good on the other end.
Testing, testing, testing.
Perfect. There we go.
Cool. Okay. Welcome back. Happy to be back. Happy to be talking more about math, talking about more on linear algebra, talking about more on linear transformations. This was a bit of an unexpected jump in for me to come in and present, but I'm happy to continue where we left off, because really I feel like this part of it is kind of like one of the biggest like meat and potatoes things whenever you're talking about linear transformations and matrices. We're going to be talking today about just like what happens when what can you do with two linear transformations in terms of composition, how that also turns to linearity, and that leads into the very important idea called isomorphisms. And then we're going to talk a little bit about like how these compositions and how these isomorphisms work when you start looking at the matrix representation of these linear transformations, which you talked about last time. So I'm going to start off a little differently from how Friedberg presents it. They kind of go compositions, matrix representations, isomorphisms, matrix representations. I'm going to go a little bit mixing it up. I'm going to first talk about solely in terms of linear transformations, and then we're going to turn all that stuff we develop into our world of matrix representations and use that to talk about matrix multiplication. So, last time on Dragon Ball Z, we talked about what's a linear transformation. And these really are the functions that we care about whenever we're talking about two different vector spaces. So if we have a vector space V and a vector space W over some common field F, recap that a linear transformation satisfies two properties. It preserves vector addition, meaning that if I take a sum and run it through a linear transformation, it'll turn into a sum in my codomain. And it also preserves scalar multiplication. So if I take a scalar product with a vector, run it through T, then it'll turn into that same scalar times the output. More generally, linear transformations take linear combinations in V and turn them into linear combinations in W. So if I have a linear combination here where all these vectors here are in V and all these lambdas are in my field, then it'll turn into a linear transformation of the images of all of these vectors in V. And that's kind of like the big definition we had last time, and that's where we developed all of our information and intuition from. And from there, we kind of proved a couple of different facts. So the first fact that we proved, which I'm going to use time and time again, is that any linear transformation is uniquely defined by what happens to a basis of the domain. To be a little bit more specific, if I have a linear transformation T from V going on to W, and if I have a basis of V, the rest of the definition of T depends on what happens if I apply it to a basis of V. And actually from that, if I can define an association between a basis of V and really any set of vectors in W, then I can extend that into a linear transformation. We also proved the rank nullity theorem, which helps gives us a relationship between the dimension of our domain, the dimension of our range, and then the dimension of our null space or our kernel. And to recap on that, the kernel, which I'll denote by ker, or null space, of a linear transformation T is the set of all vectors which get sent to zero by my transformation. Our third thing that we proved is kind of turning our linear transformations into matrices and giving that association between them. So any linear transformation can be represented by a matrix whenever you're given two ordered bases, one for the domain, one for the codomain. And then finally, linear transformations between two vector spaces form their own vector space, and we denote that by L, V, comma, W, all linear transformations going from V over to W. And really, this third bit here, number 3, is where we kind of left off with both 3 and 4. And I want to spend a bit more time talking about this association because I feel like this gives a big, strong case for like everything else we're going to be talking about today. So let's start with the linear transformation T. Let's say I have two ordered bases, B1 and B2. B1 is an ordered basis of V, B2 is an ordered basis of W. To recap, the matrix representation of T in terms of B1 and B2 is this M by N matrix T B1 B2. It's generated by setting the ith column vector into equal to the coordinate vector of whatever happens to the ith vector in our basis B1. So whatever T transforms VI into, I can take all of those scalars from expanding it out in terms of B2. I can turn that into a vector within the FM. So all vectors of length M. Taking all those coefficients, I can turn it into what we call the coordinate vector, and having that be my ith column of this matrix here. So our big thing that we showed last time was if I have a linear transformation, I can generate a matrix representation. Now I want to start thinking about, can I do the opposite? Can I take a matrix and turn it into a linear transformation? We're going to start with one way, which is a bit more technical. It has a bit more awkward of a structure to start with. And then at the very end of the session, we're going to talk about a different way of turning a linear matrix into a linear transformation that's a lot nicer and plays with what we're going to develop throughout the rest of the session. So if I have this basis B1 of V and a basis B2 of W, this is going to be an M by N matrix because T is going to go from V to W. My domain has a dimension of N. My codomain has a dimension of M. I produce an M by N matrix. I can define a linear transformation given some M by N matrix A by letting the jth vector in my basis of V become this linear combination here in terms of my basis in W. And the scalars that I'm using are all going to come from the jth column of A. So if I have, let's say I do let's do like a 3 by 3 matrix just to give like a little bit of example of what I'm doing. Let's say I do like 3, 7, -2, 1, 0, -5.
If you're writing on the screen, we cannot see what you're writing on the screen.
Give me just a second to fix that. Let me stop sharing my screen and then I'll try doing it again. I thought I shared my entire screen. Okay. Tell me if you could see this.
Yep, that looks good.
Cool. Okay, I guess I shared the window on accident. Okay. Let me go back to my train of thought. Okay, so what I'm doing here to define this linear transformation in terms of my matrix, I'm taking the jth basis vector of B1, and I'm basically forcing it to map to this linear combination in terms of B2, where all of my scalars come from that jth column. So so this expansion here is basically expanding over all of the rows of my matrix A. And so when I'm going through all of that and I'm fixing my column, I'm really just taking all of my entries in that jth column of A. And basically by doing this, I am forcing that jth column to be this coordinate vector here. And so really by forcing this definition, I'm creating a linear transformation so that when I take my matrix representation of T, I end up getting back my matrix. So I have this back and forth that I've started to develop where I can go from a linear transformation to a matrix representation, or I can go from a matrix to a linear transformation. And this is just like a forceful definition. We're going to talk about a much more elegant map at the very end of the session, but this is at least like a start to say, hey, I have a counterplay going from like one vector space to another. So I want to talk about these as functions. So as a little recap on notation, let big M of Mn of F, this is the vector space of all M by N matrices with entries in F, and then L of VW right here is the vector space of all linear transformations going from V to W. So I'm going to start by denoting by this capital phi right here. This is a map going from linear transformations to matrices. And so what I've got going on here is this map, I'm just saying, is the map that sends a linear transformation to its matrix representation. The map I just defined, I'm going to call capital psi. And so what I want to ask is, how do these two maps interact with each other? Is this really like the back and forth that I want? So I'm going to quickly recap what is a composition of two functions. And this is going to be important for using just for like the rest of the session. So if I have three sets in general, A, B, and C, and then two functions F going from A to B, and then G going from B to C, the composition of these two functions, F and G, I can define as this function G of F going from A to C, where it's basically I'm taking an input, running it through F first, and then running it through G. So I can think of this as a two-step process where I'm going from right to left, applying each function one at a time. So really, compositions of functions are basically whenever I take a sequence of operations and I apply them one at a time, going through one another. I like thinking of compositions as just like, here's a sequence of things that I am doing. So let's see what happens when I compose these functions. So let's start with doing phi first and then applying psi. So phi is my map which takes my linear transformations and turns them into their matrix representations. So let's say I have some linear transformation T going from V to W. B1 is my ordered basis for V. So if I were to apply T to each of my basis vectors, I'm going to get some linear combination of these Wi's right here. And all of these Wi's belong to a basis of my basis B2, which is a basis of W. So kind of by definition, I'm forcing the ijth entry of my matrix representation to be this scalar lambda ij. So T is uniquely defined by these scalars. So what ends up happening is I'm taking phi is going to take T to its matrix representation. And then if I were to try and find the linear transformation defined by this matrix, well, it just has to be T again, based off of how the matrix representation is defined. So really, psi undoes whatever phi does. So if I take a linear transformation, turn it into its matrix representation, and then send it back to a linear transformation, I'm going to get the original thing, which makes sense because these are really like one and the same. If I were to go the other way, let's say I have a matrix A, I'm going to let the linear transformation that we generate from A, I'm going to call it T sub A. I want to find what the matrix representation of this linear transformation is. So I specifically defined it so that if I apply T sub A to the jth basis vector, then the coordinate vector just has to be the jth column of A. So really, the matrix representation of this linear transformation is equal to the matrix I started with. So this implies if I reverse my composition, phi is going to undo whatever psi does. So psi will take a matrix to a linear transformation, and then phi will take it back to the original matrix. More formally, if I look at these compositions, psi composed with phi, or psi of phi, this is the identity map on my vector space of linear transformations. And then if I do phi composed with psi, I get my identity map on my vector space of m by n matrices. So this specific property here, where composing them gets both of these identity maps, is what we call invertibility, and I want to review that a little bit. So if a and b are sets, a function from a to b, we can call f, is invertible if there exists another function g going from b to a, so I'm reversing the domain and codomain, such that when I compose each of them, I get the respective identities. So if I can think of this in terms of a little diagram. If I'm going from a to b, doing my f, and then going back from b to a using g, ideally what happens is if I skip over, I just do nothing. And that's my identity function on a. And then similarly, if I were to do g first then f, giving me this other little chain right here, skipping over is also equivalent to doing nothing. So, some quick properties. If a function g exists, which is an inverse of f, then it's unique. And so we can denote it by the special notation f inverse x to the negative 1. This is not the same as 1 divided by f. This is special notation for functions. And we're going to call this the inverse of f. So some quick little facts here that are also useful. If f is invertible, then the inverse of f is also invertible. So the inverse of the inverse is equal to the original function. If f and g are invertible, then the composition of two invertible functions is also invertible. If I were to take the inverse of this composition, what ends up happening is I reverse my composition and look at f inverse composed with g inverse. And then finally, a function is invertible if and only if it's what we call bijective, meaning that it's both injective or one-to-one, which basically means if I have two unique outputs, then it's two unique inputs that I have to give them. And then surjective basically means that the entire codomain is equal to the range, meaning everything in my codomain gets mapped to. So what we really just showed in our last set of slides right there is that phi and psi are both inverse functions. So in particular, because they both undo each other in that way, the inverse of phi is equal to this psi right here. So my association to a matrix representation, I can undo that and get back the linear transformation. And then if I have a linear transformation coming from a matrix, then I can undo that with a matrix representation. So I have from this a one-to-one correspondence, which is the same as a bijection, between linear transformations and matrices. Really what I can say is that this vector space right here and this vector space right here are really one and the same. And I can kind of go further and say not only are they the same as sets, but they're the same as vector spaces. They're just different coats of paint on one another. This idea is really useful in general, getting invertible linear transformations. And the reason for that is it allows us to really consider a lot of these like various abstract vector spaces as the same. Or I can solve one problem in terms of another vector space which has this invertible linear transformation going between it. And from there, if I can solve it in one context, I can solve a problem in another context because these are really the same quote-unquote vector space here. I want to look at the chat, see if there's any questions before I move on, because I know what I did is really, really technical. Okay, I'm seeing in the chat here. Yeah. This F inverse that I was talking about, this is not reciprocal. This is saying this is the inverse. I know there's negative powers, which mean you should take the reciprocal, but this isn't really a power. This is just fancy notation. What else do we have? 5 times psi is 1. Actually, going into technically reciprocals and inverses would be the same. Yes. Yeah, in the sense of like inverses being reciprocals is like two different names for it. Like it's technically a division, but I don't want to talk about it as like this is dividing. But yes, we are gonna talk. Yeah, we're gonna talk a little bit more on just like whenever we have these like inverse transformations, and it does turn out that this vector, or not specifically this one, but if I have, there's a special group called the automorphism group, which I might talk about a little bit. I'm not getting too in depth with that, but the idea of like if I have a bunch of invertible linear transformations, composing them together makes it something called a group. I'm going to move on to the next slide. So let's talk a little bit about compositions. So fancy notation wise, oftentimes whenever you have two linear transformations, so I have t going from v to w, u going from w to x, rather than writing u of t like this, we're going to write just ut. We're going to write it in terms of multiplication notation. So what I want to show as our first proposition is if I have two linear transformations, then the composition is also linear. And this is a pretty quick and dirty just application of like, do you know the definition of a linear transformation? So if I have two vectors v and w, and then a scalar lambda, and I apply the composition to lambda v plus w, I first apply t to this combination, and since t is linear, I can split it up as so. This just comes from the fact that t is a linear transformation, and I'm applying it first. And then I'm skipping a little bit in between here and here. For this little intermediate step, I can say that this guy, u I can split up as a sum over the sum. So I could do u times lambda t of v plus u t of w. And then from there, I can pull out this scalar and achieve this result right here. So really what I'm able to do is take a linear combination like that, lambda v plus w, and then split it up over t and u individually to show that the composition also is linear. So really the goal of this is just do it one at a time. So quick properties. I'm not going to go fully into the proofs of these because a lot of these are just using the definition. I wanted to show the last one because it's like a very core idea. But all of these here are pretty much just like go through the motions. This is theorem 2.10 in the book. I believe the last one was theorem 2.9. I would need to double check the numbers. But here, this is the more generalized version. Theorem 2.10 in the book only talks about it for just one vector space, which makes it a little simpler. This is, I believe, one of the exercises. So I have a linear transformation t going from v to w. I have 3 linear transformations here going from x to v. I'm really defining these just so the compositions work. And then I have 2 linear transformations s1, s2 going from w to x. So you don't have to worry too much about like what's the domain, what's the codomain, and whatnot. Really, I'm just defining these so that I can properly define composition. So we can define the sum of 2 linear transformations by just saying, oh, the output is the sum of the outputs. And so if I compose a linear transformation with a sum, then I have this distributive property going on where it's the sum of the compositions. And this works both directions. So if I compose it on the left or if I compose it on the right, it distributes both ways. The second thing to look at is that composition is associative. This is more of a function idea rather than necessarily a linear transformation idea. But it's basically saying if I do u2, then u1, then t, that's the same as doing u2, then u1, then t. This is the associative property, is just telling us like what order we want to apply things, and it works both ways. And then finally, if I have a scalar lambda, then I can think of this as, if I scale the composition, I can think of it as the composition of one of the linear transformations and a scaled version of it. Doesn't matter which one I go into. So I could either have it be scaling t, or I could have it scale u, and it works the exact same way. So really, compositions like this kind of work like a funky little multiplication between two of our linear transformations here. So going into inverses, this is theorem 2.17 in the book. If I have an invertible linear transformation, then the inverse, T inverse, is also linear. And the way to go about this is basically just using the idea that I can say T is a bijection. So if I have two vectors, W1 and W2 in W, T is invertible, making it a bijection. So I can find unique vectors in V, V1 and V2, such that V1 maps to W1 under T, and then V2 maps to W2 under T as well. If I have any scalar lambda, then if I were to apply this to my sum here, lambda W1 plus W2, then I can turn W1 and W2 into their images under T. And then from here, I know T is linear. So I can recompress it and grab everything again and turn this into T of lambda V1 plus V2. But then since T and T inverse are inverses, they just cancel each other out. And so what I'm left with is this linear combination that I got here. But I know that V1 is what maps to W1, V2 is what maps to W2. So using my inverse function, I have that V1 is equal to T inverse of W1, and then V2 is T inverse of W2. So just renaming these two, I have that this is a linear transformation. So really, I was just able to use the fact that, hey, because T is invertible, it's a bijection, meaning I can go backwards and talk about stuff in V, and then use the fact that T is linear in order to get to what I want. So if I have an invertible linear transformation, we have a very special name for these types of linear transformation. This construct in general pops up in all sorts of different fields of math, usually under the same name. If you look at something called category theory, you'll see it as like the name for it. I know in topology in particular, we don't call it an isomorphism, we usually call it a homeomorphism, but it's the same idea. So if I have two vector spaces over a field, these two vector spaces are what we call isomorphic if I can find an invertible linear transformation going from V to W. And we call this invertible linear transformation an isomorphism. So this part that I'm going to get into isn't proved in the book. This is more like a comment, but I feel like this is such like a nice thing to talk about when you're talking about comparing two vector spaces that I want to like go into more depth with it. So I want to redefine what's called an equivalence relation. So if I have a set X, I can define an equivalence relation as just a relation between pairs of elements within X that have the three following properties. So the first one is that any equivalence relation is reflexive. So X is related to X for any element you pick. Anything is related to itself. The relation is symmetric, meaning that if I have two elements where like X is related to Y, then I have to say that Y is related to X. And then finally, any equivalence relationship is transitive. So if I have that X is related to Y and Y is related to Z, then X is related to Z. These three properties allow us to kind of talk about relationships that act like equality. I'm not strictly saying that these two elements are the same, but if I have any relationship which has these three properties, then I can kind of group together things that act the same way in context. Probably one of the most useful, or like things that pop up the most in terms of an equivalence relationship, is modular arithmetic. So if I have that two integers are congruent modulo some integer n, then I'm able to, then this right here is an equivalence relationship. So if you don't know about modular arithmetic, you can think about like clock math. So if I were at 3 o'clock and then I were to go 12 hours into the future, I'm still at 3 o'clock, even though it switches between AM and PM. The idea here is if you have two numbers that are congruent modulo some number, then they're the same in terms of divisibility. They're not the same number, because like 3 is congruent to 15 modulo 12, but they're really the same if you think about it in terms of divisibility. And these equivalence relationships pop up all throughout math. And it's very helpful to talk about saying two things are equivalent within a certain context. And here we're going to talk about it between vector spaces. So if I have two vector spaces over a field F, this is exercise 2.4.13, I can write V, I'm going to say is isomorphic to W. If the vector spaces are isomorphic, we use this congruence symbol if you've seen it from geometry. This relationship here between two vector spaces is an equivalence relation. So I want to be able to show that it's reflexive, meaning every vector space is isomorphic to itself. I want to show it's symmetric, which really means if I have an isomorphism from V to W, then I have one from W to V. And then finally, I want to show that this is transitive. If I have an isomorphism between V and W and an isomorphism between W and X, then I can find one between V and X. So, first one's really chill. Any vector space is isomorphic to itself by just using the identity map. And the identity map, for if we need a refresher, the identity map just takes an element and sends it to itself. So really, it does nothing to anything. You just put in an element and it spits it right back out. This is linear. This is bijective. Therefore, it's an isomorphism. Second off, isomorphism or isomorphicness between vector spaces is symmetric, because if I have a isomorphism T, then T inverse is linear, which we just showed, and it's invertible because the inverse of T inverse is T. So that makes it an isomorphism. So if V is isomorphic to W, then W is isomorphic to V. And then finally, to show that it's transitive, I can just say if I have two isomorphisms T and U, I can take the composition. The composition is invertible because if I do UT inverse, that's equal to T inverse composed with U inverse. This is linear because compositions are compositions of linear transformations are linear. This is invertible, so therefore this is an isomorphism, and so we have that V is isomorphic to X. So this shows that being isomorphic is a way of equating two vector spaces together. And so, kind of tying it back to general set theory, we have the idea that if a bijection will only exist if and only if two sets have the same cardinality or the same size. So the same is true for vector spaces, meaning like if I have an isomorphism between two vector spaces, then those vector spaces are the same size. I can be a bit more specific and say that if I have an isomorphism between two vector spaces, then their dimensions are the same, meaning they have the same size basis. So this here is theorem 2.19 in the book, and let's run through that real quick. So if I have an isomorphism T, it's injective and it's surjective. Last time we proved that a linear transformation is injective if and only if its null space or its kernel is trivial. The null space is every element that gets sent to 0 in the image. So in this case, if I have an isomorphism, it's injective, so the only thing that gets sent to 0 is 0 itself. Since T is surjective, I can say that the range of T is all of my codomain here, W. Going through the rank nullity theorem from last time, the dimension of my domain is equal to the dimension of my null space, which is the nullity, and then plus the dimension of my range, which is what's called the rank. So since the only thing in my null space is 0, this guy right here is just equal to 0. The dimension of like the trivial vector space is 0. And then this guy right here, well, the image of T is the same as all of W. So this right here is the same as that. So this shows that if I have an isomorphism, the dimensions of the vector spaces are the same. Following that up, let's say I have two vector spaces with the same dimension. So let's say B1 is a basis of V, B2 is a basis of W. I can force an isomorphism to happen by just sending V1 to W1. I can send V2 to W2. I can send Vn to Wn. And then from there, since I have a map between bases, I can extend that into a linear transformation. And then I can just define the inverse by reversing my map, because these are the same. So W1 gets sent to V1, W2 gets sent to V2, Wn gets sent to Vn, and then extending it linearly. So I'm kind of just forcing a linear transformation to happen, and then by composition, and by the way like I'm forcing things, if I were to compose them, I would just get the respective identities. So if I were to do T inverse and T, I would get the identity on V, and then if I did T with T inverse, I get the identity on W. And so I'm just forcing an isomorphism to happen if I have two equally sized bases. So as a corollary, in the very beginning of the talk, when I was talking about how I have an invertible linear transformation between my set of linear transformations and my space of vectors, or matrices, m by n matrices, m of mn f, this defines an isomorphism. Because making a matrix representation is a linear transformation. Going from the matrix to the linear transformation is a linear transformation. Those are invertible. So these two have the same dimension. So because I have this isomorphism going on, the dimension of my space of linear transformations is equal to m times n. And the way you can really cement that and calculate that is just find a basis of your set of m by n matrices. And you can find, I'll show a basis for, let's do m2 by 2 over, really it's over any field, but I'll do it over the real numbers. A basis for this is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1. So this vector space has a dimension of 4. So if I were to do the set of linear space of linear transformations between two vector spaces of dimension 2, I have that's a dimension of 4. So, beginning of the session, we talked about linear transformations are isomorphic to set of all m by n matrices. So any linear transformation, I can really consider it to be just the matrix representation. Because I have this isomorphism, I can really think about these as like the same vector space. So I can, if I have a problem regarding linear transformations, I can turn that into a problem regarding matrices. And so if I solve it with my matrices, then I can solve it in terms of my linear transformations. And this is especially nice because because we have a linear an isomorphism specifically, all of the properties of my one vector space in terms of like vector addition, scalar multiplication are the same here with these operations. I would have to reframe them a little bit, but it's not that hard to go from one context to the other whenever I have a linear isomorphism going on. So being isomorphic really turns two vector spaces into the same thing. Or in other words, one vector space is just the other one with a fresh coat of paint. And I want to take a second to stop here, look and see, are there any questions in the chat? Any questions about anything we talked about so far? Because I know I've gone through this pretty quickly. And I know this is like a key idea that I want to just like sit on and like hold. Anything in Twitch chat? Cool. Okay. Let's scoot on over to really actually another important idea, kind of going into the same idea of I can think of every linear transformation as a matrix. Now I'm going to think about every vector space period as a vector. So if I have a vector space of dimension n, then I can say it's isomorphic to Fn. So this is the vector space of all n-dimensional vectors with entries in F. Because these have the same dimension, these are isomorphic. And I can talk about a very specific map to get here. So if I have an ordered basis of V, then I can turn every vector in this basis here into the corresponding standard basis vector. And to kind of recap what the standard basis vectors are, the ith standard basis vector of Fn, this is the vector where the ith entry is 1, every other entry is 0. So the standard basis for, like, let's say F3, that would be 1, 0, 0, 0, 1, 0, and then 0, 0, 1. So this would be E1, this would be E2, this would be E3. So mapping my ordered bases to each of these standard basis vectors really creates the map where I'm sending a vector to its coordinate vector. And so this map I'm going to denote by phi sub b, and we're going to call it the standard representation of V with respect to B, V being my vector space here. This is a linear transformation, and it's an isomorphism. We talked a little bit about this relationship in our last session. We talked about how it's linear, and to show that it's an isomorphism, I can kind of just do what I did before and show, hey, I'm going from one basis to another basis of the same size, so that means it's an isomorphism. So really, any abstract vector space that's finite dimensional can be thought of solely using these coordinate vectors. So being able to think about vector spaces in this way and think about linear transformations as matrices, it gives you a lot of leg room in order to compute things and in order to like computationally figure out problems about more abstract spaces. So Fn is really nice for doing a lot of your legwork, doing a lot of your like computations if you can't like abstractly think about a problem. So let's go back and talk more on these matrix representations. So we talked about composition. We talked about how if we compose two linear transformations, I get another linear transformation. So I want to figure out what happens if I take the matrix representation of a composition. So I'm going to I have two linear transformations, T from V to W, U from W to X. B1 is the basis of V. B2 is the basis of W, and then B3 is the basis of X. So I'm going to let A be the matrix representation of U. I'm going to let B be the matrix representation of T. And so for all J going between 1 and N, I'm looking at my basis vectors of B1 here. If I were to apply the composition to this Vj, I can start by saying, well, applying T to Vj gives me this linear combination right here in terms of vectors in W, going from 1 to M. And all of the scalars are determined by my matrix representation B. And then if I apply the fact that U is linear, I can turn it into a linear combination in terms of images of the WKs under U. But then I can play the same game again and represent this in terms of the coefficients of A. And these here basically come from the fact that the way that I define my matrix representation is by using the coordinate vectors of the images of these basis vectors. So now what I want to figure out here is just, what is this double sum? Can I simplify this? Can I make this a little nicer? Because this is pretty computationally intensive, and I just want to take a slide to run through the math of simplifying it and making it nicer. So pause to let my throat take a rest. So I'm going to start. This is that last sum that I had at the end. I'm going to just write this out in a more expansive form. So I'm going to take it from its series representation, turn it into a full sum. So what I'm doing here is I'm really fixing the kth column, and then I'm expanding about the rows. So I'm going through that kth column and looking at all my basis vectors of my big vector space X. And all of these are being multiplied by this entry in the kth row, jth column of B. So what I'm going to do now is I'm going to take these entries and I'm going to distribute them. I'm going to distribute them to all of my entries in my sum. And I'm going to get something that looks like this. This is just me multiplying everything on the inside, and I'm taking the sum of all of those. So now what I'm going to do, I have this giant sum of a giant sum. I'm going to turn it into smaller components. And so I'm going to turn basically distributing this sigma right here. And so what I'm doing is now, rather than looking at it as a sum of a giant sum, I'm turning it into a sum of smaller sums. And so since this is just a normal vector, and this doesn't really depend on what I'm summing over, this doesn't depend on k, I can factor out each of these x1s, x2s up till xp. And then at the very end right here, these are all scalars. And so I'm going to compress it back into a summation form where it's the sum going from 1 to p. I know this is a lot to take in. I want to give everybody a second to run through the ideas, and really I want to give myself a second to sip some water. My throat's a little dry. Because I know this is a lot. I know when I saw it first, in the textbook, it went from this right here immediately to this right here. And I know double sums can be a lot, so I want to take time to just let's digest this, especially because this guy right here is going to be really important for when we define matrix multiplication. Cool. So let's talk about that guy. So this right here should be x sub I. There we go. So what I'm doing with these coefficients here is this is from my matrix representation of U. This is my matrix representation of T. And what I'm doing here is I'm going through the ith row of A. I'm going through the jth column of B. And I'm multiplying every corresponding entry. So the first entry in the ith row of A is being multiplied by the first entry in the jth column of B. Second entry, third entry, all up until I get to M. So with this definition, I've generated a brand new matrix. And so this matrix C is my matrix representation of U composed with T. And that's going from basis 1 to basis 3. And so using this, I can define a way to combine two matrices of compatible sizes, turn them into something new. So if I have an M by N matrix, I have an N by P matrix, the product denoted by AB, this is what we get, an M by P matrix, where every entry in the ith row jth column, I take the ith row entries of the ith row of A, entries in the jth column of B, multiply them correspondingly, add everything up together. So the reason why, so refreshing my words, in order to have a compatible product, I specifically need the number of columns of my first matrix to match the number of rows of my second matrix. And the reason for that is, in order to define a composition, I need the codomain of one linear transformation to match the domain of my second. Really, that's just for functions in general, but here specifically in terms of my linear transformations, I need that. So really, as a proposition, and really we saw the proof of it because we defined it in this way, if I have two linear transformations going from V to W, W to X, T and U, I have three ordered bases B1, B2, B3 of V, W, and X respectively, then the matrix representation of the composition is equal to the product of the matrix representations. So matrix multiplication is secretly just matrix representations of compositions. So compositions, in going back to my idea of isomorphisms, going to my space of linear transformations, I have compositions. Going into my space of matrices, since these two are really the same thing, my equivalent of composition is this matrix multiplication. And so these are one in the same. To kind of like give a nice visual on this, I really recommend, if anybody hasn't seen it, 3 Blue 1 Brown has a series of videos on YouTube for Essence of Linear Algebra, and he does a way better job of like explaining like the visualization and the processes behind this. And he has a particular like really good video on the association between matrix multiplication and composition of linear transformations. It's really, really cool. So I just want to go through a quick little example just in case people haven't seen multiplying matrices before. So I got this matrix A, this matrix B, 2, negative 1, 5, 3, negative 3, 0, 1 for A, and then 1, 4, 0, negative 2, 3, 7 for B. If I want to multiply A and B together, let's kind of go through that definition again. So going step by step, let me make this a little bit thicker so that I can actually like properly highlight. Cool. So in order to get each element, this is a 2 by 3. This is a 3 by 2. I'm going to get a 2 by 2. So the way I produce each entry is I'm going to go first row times first column. So I do 2 times 1, which is 2. Negative 1 times 0, which is 0. 5 times 3, which is 15. 2 plus 0 plus 15 equals 17. And I continue that process for each other column in my second matrix. So 2 times 4, which is 8. Negative 1 times negative 2, which is 2. 5 times 7, which is 35. 8 plus 2, that's 10. Plus 35, that's 45 right here. And now I keep on going. Negative 3 times negative 3 times positive 1 is negative 3. 0 times 0 is 0. 1 times 3 is positive 3. Negative 3 plus 0 plus positive 3 is equal to 0. And then finally going through that second row, second column, negative 3 times 4 is negative 12. 0 times negative 2 is 0. 1 times 7 is 7. Negative 12 plus 0 plus 7 equals negative 5. And this process, like actually going through it, kind of shows why we need these sizes to be the way that they are. Because if I were to multiply two sizes that like just weren't compatible, then I'd either run out of room or I would have too much stuff. And I couldn't properly combine them into a single element. I'm going to run through this a little bit quicker. 1 times 2 is 2. 4 times negative 3 is 12. Add them together, you get negative 10. 1 times negative 1, negative 1. 4 times 0, 0, negative 1. 1 times 5 is 5. 4 times 1 is 4. 5 plus 4, 9. Continue this process, get 6, 0, negative 2, negative 15, negative 3, 22. So in particular, this kind of shows that matrix multiplication isn't commutative, meaning I can't swap it freely. In this example, I get two different matrices of two different sizes. But even if I were to like somehow get, I don't know, construct it to where like this doesn't exist, I just get this on the inside, like shrink down my sizes. Those aren't the same entry. And this makes a lot of sense because in general, compositions of functions, that's not commutative either. I can't necessarily do one thing then another and expect to flip them and get the same result. That's not necessarily true in general. So I want to talk about an example with multiplying matrix representations and showing, hey, the composition works as we think it should. So to kind of recap, these spaces here, this P3, P2, these are all polynomials with coefficients in this case, the real numbers, of degree less than or equal to whatever the subscript is. So this is degree less than or equal to 2 right here. This is degree less than or equal to 3 right here. So if I'm going to define u and t going from one to another. U is my derivative. T is going to be the integral from 0 to x of f of t dt. So from calculus, this is FTC part 1, I believe. I always mix up the part numbers. If I were to take the derivative of this integral right here, I'm just going to get f evaluated at x. So I can verify this using matrices, in particular for the special case of like polynomials of these sizes. So I'm going to take my standard ordered bases of each of them. So for P2, 1x x squared, that's a basis. And then for P3, I get 1x x squared x cubed. If I were to look at the matrix representations, I just have to figure out, okay, what does everything become under these transformations? So U is going to take 1 and send it to 0. So the coordinate vector of that is just 0, 0, 0. X is going to be turned into 1. The coordinate vector that I'm going to say is 1, 0, 0. X squared is going to be turned into 2x. So my coordinate vector there is 0, 2, 0. And then x cubed is going to be turned into 3x squared. So I get this coordinate vector 0, 0, 3. And then kind of reversing it with my integral here. 1 is going to turn into x. X is going to turn into 1/2 x squared. X squared is going to turn into 1/3 x cubed. That's where I get these vectors from. So let's look at the product of these two matrices together. So where did my slide go? I guess I'm doing it on here. So if I were to do U times T, yes. So let's write it out. If I'm doing 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0 times 0, 1 times 1, 0 times 0, 0 times 0, add those all up, I'm just going to get straight up 1. I'll put it over here. Going through the second column, really this guy is the thing that's going to determine what my value is. And this is going to go with 0. Everything else is 0, so it doesn't matter. So I'm going to get 0. And then same idea right here. This is going to match over here. But that'll just give me 0 for everything. So I'm going to get 0. Going with this second row. Let me erase that. Let's multiply. So this guy right here should match with this entry right here. That'll give me 0. Everything else is 0, so everything else will be 0. So this is a 0. If I go through the second column, however, ugly. If I were to go through the second column, this 2 right here is going to match up with the 1/2. And then the zeros are going to match up with each other. 2 times a half is 1. 0 plus 0 plus 1 plus 0. That's 1. But then I'm going to get the same fate again for my third column where it's 2 times 0. And then everything else is 0. So I'm just going to get myself 0. Finally, I'm going to get the same deal. The only non-zero thing it'll match up with is the 1/3. 3 times 1/3 is 1. So I'm going to get this row being 0, 0, 1. And this right here, we're going to talk about the identity matrix in a second. But if I were to look at this as a matrix representation, this is the matrix representation of the identity map on my polynomials of degree 3 or less. Yes, because I'm differentiating first to go to P2 and then integrating to go back to P3. Yeah, cool. Other way around. Never mind. So this is kind of giving us exactly what we thought. Where it's, if I take the derivative of the integral, then I'm getting f of x. But what happens if I were to do the other way around? I integrate first and then, or if I were to differentiate first, then I integrate. So I'd be doing this matrix here times this matrix. So let's run through and go through the backwards process. This will be a 4x4 matrix. Here's immediately where we're going to get to a little bit of an issue. My first row up here is all zeros. So no matter what I do with these columns, it's just going to die and turn into all zeros. So I'm going to get 0, 0, 0, 0. Running through that second row times all the columns, I got 1, 0, 0. So I'm only going to preserve that first entry. So I'm going to get 0, 1, 0, 0. Third row here, the second entry is going to get halved. So 0, 0, 1, 0. And then finally, this third entry right here, because of how my fourth row is written, the third entry in each column is going to get thirded. So that'll be 0, 0, 0, 1. So I don't have the identity map as I wanted. And kind of the reason for that is if I were to differentiate any constant function, or just any constant, I'm going to get 0. And then since this right here is a definite integral, well, that's the even though it's taking like a variable bound, the definite integral of 0 is just 0. So this is always going to be sent to 0. Another way you can think about it is a linear transformation always maps 0 to 0. So I get the identity one way, but not necessarily the other way. So that matrix representation of the identity map pops up a ton. So we're going to give it a name. So the first thing I want to talk about is what we call the Kronecker delta. We call this delta ij. The way that this works is if my indices are the same, this is going to turn into 1. If they're different, it's equal to 0. So if I do delta 2, 2, that's equal to 1. If I did delta of like 3, 5, that's equal to 0. As long as they're the same indices, it's equal to 1. If they're different, it's equal to 0. It's basically a function which checks, do these two things match? So the n by n identity matrix, which we're going to call I sub n, is defined to where the ijth entry of the identity is this Kronecker delta. So if I were to think of it in terms of specific entries, everything along the main diagonal, so 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, that's all ones. And then everything else is 0. So as we saw in our last example there, we got the 3 by 3 identity. So 1, 0, 0, 0, 1, 0, 0, 0, 1. This is what we call I3. So note, if I have a vector space V, that's dimension n, some ordered basis B, if I were to look at the matrix representation of the identity map, I get the n by n identity. So, want to show some quick properties of matrix multiplication. I'm not going to fully go into the proofs here, solely because this is just the equivalent of what we saw before for linear transformation compositions. So really the ideas behind them are the exact same, and we've we were able to look at those before. So if you can prove one, you can really prove the other. So the way that it works, if I have an n by n matrix A, I have two n by p matrices B and C, and then two q by m matrices D and E. Basically make the sizes appropriate so you can actually multiply them. Matrix multiplication distributes both ways. So if I do A times the sum B plus C, I get AB plus AC. If I do the sum D plus E times A, I get DA plus EA. I can scale, if I'm scaling a product by a scalar, I can scale either individual one. And then finally, if I have the identity matrix I sub n or I sub m, whatever dimensions you need in order to properly multiply it, it's going to preserve your matrix because it's the identity map. Composing with the identity map doesn't do anything. And then this is theorem 2.16 right here. Matrix multiplication is associative. So just like compositions of functions, I can do it, and I could do a series of 3 in any order I want. This all basically holds because it holds for linear transformations. So now I want to go into a little bit of multiplying vectors by matrices. So I can do a matrix vector product by just thinking of a vector as an n by 1 matrix. So if I let A be an m by n matrix, B be an m by p matrix, I'm going to let U sub V be the jth column of, or U sub J be the jth column of the product, V sub J be the jth column of B. So this proposition here is saying, if I were to multiply this matrix A by the jth column of B, I'm going to get the jth column of AB. And then second, if I were to multiply the jth standard vector of FP by this matrix B, then I'm going to end up getting the jth column of that matrix. So if I were to multiply a matrix by a corresponding standard vector, I can get that column out. So the first part's a little technical. So thinking about how uj is defined, this is the jth column of AB. So running through, I have, and like representing it as like a full vector, this is the entry jth column first row. This here's jth column second row, jth column mth row, going like all the way through. To kind of recap, we have to clarify, AB is an m by p matrix, because this is m by n, this is n by p. So thinking about the definition of matrix multiplication, I can write this as, okay, take all the entries in my row, multiply by all my entries in my column. So here I'm preserving my first row and then preserving my jth column of B. Second row, jth column. Nth row, jth column. So going through this, Well, if I were to look at how we define matrix multiplication like times a vector, really what I'm doing here is I'm just multiplying A out by this column vector here of all the B's and of the jth column of B. So what's going on right here is that this is just the definition that I want, because I'm running through each of my rows, multiplying by that singular column. And so from this is just like the definition of matrix multiplication. So to talk about our second claim, if I want to think about B times my jth standard vector, this is an n by 1 vector, since B is n by P. The ith entry of this is just going to be the jth entry of my ith row. So, which is just my Bij. If I were to take all these entries and like put them together into a vector, I'm just going to get my jth column, because everything in here is 0 except for that singular 1 at the jth spot. So it's going to take the jth entry of it's going to take the jth entry of each row, but that would just make the jth column. So that means this has to equal the jth column of B. Taking a second, seeing if there's any questions in the chat. I know this is a little funky. This is going back here. Any questions in the chat? I don't see. Cool. Okay. Cool. Okay. So another proposition, really, I can, to kind of hammer down like this association between vectors and Fn, and then linear transformations and matrices. If I were to look at the coordinate vector of a transformed vector, I can think of that as matrix representation of my linear transformation times my coordinate vector of the original vector. So V and W being finite dimensional vector spaces, order bases B1, B2 respectively, T linear transformation. No matter what I plug in, I can think of the coordinate vector of my transformed vector as matrix representation times coordinate vector. There's a different proof in the book for Friedman. I took this proof actually from Axler. I feel like it's a lot cleaner to think about, especially because we've done all these operations with our vectors and our like matrix representations anyway. So let's say it's like my domain is dimension n. If I were to take the ith column of my matrix representation, that's going to be what happens to my ith basis vector, the coordinate vector of that. So for any input, if I were to look at that as a linear combination of my basis vectors, well, my coordinate vector association, that is going to be a linear transformation. We talked about that before. That's actually an isomorphism. So I can split this up as a linear combination of all of my coordinate vectors of my basis vectors. But really, when I'm doing this, as we kind of like saw it before in like just our previous result, this is just what happens when you take my transformation, my matrix representation of my transformation, and times it by by the coordinate vectors. And so, yeah, really kind of just like by the definition of matrix representations and matrix multiplication, I get this really nice result. So really, yeah, if you're thinking about these abstract linear transformations and like applying them to abstract vectors, I can instead think of it as matrix times vector. Very computationally easy. So this is a computational way of thinking about like what happens. So I want to go back to invertible transformations. I want to talk about isomorphisms again. So if we have an invertible linear transformation, I can spin that and talk about, okay, what's my analogy in my matrix space? So if I have a square matrix, n by n matrix A, I can say it's invertible if I can find another matrix B such that A times B and B times A is equal to the identity. Such a matrix is going to be unique. We call that the inverse of A. Call it A inverse. We specifically need a square matrix because whenever you have an isomorphism, the dimensions of your domain and codomain are the same. So that means you're going from vector space of dimension n to another one of dimension n, meaning your matrix representation is going to be n by n. So, as you would assume, if I were to find an isomorphism, linear transformation is an isomorphism only if its matrix representation is invertible. And if I were to take the matrix representation of the inverse, that's equal to the inverse of the matrix representation. So, to prove this, let's start by assuming, hey, we have an isomorphism here, T. That means the dimensions are the same, so this is going to be a square matrix. Cool. So I can find an inverse function, T inverse, compose it both ways, get two identities. We know that the matrix representation of the identities are just the identity matrix. So if I were to multiply matrix representation of T inverse by matrix representation of T, I can pull it back together and say, well, it's the matrix representation of the composition, but that's just the matrix representation of my identity, which is my identity matrix. And I can do that in the reverse and show that if I do T times T inverse, I get the identity matrix again. So my matrix representation is indeed invertible, and then the representation of the inverse is the inverse of the representation. Conversely, let's say I have an invertible matrix representation. If the inverse exists, I can find an inverse to that matrix. From our very beginning discussion, I can turn any matrix into a linear transformation, where the representation of that linear transformation is the matrix I had. So I can turn B right here, this inverse, into a linear transformation U. And when I end up composing them, I can split it up. So the matrix representation of the composition is equal to the product of the matrices, but these are inverses. So that means I get the identity. And then in reverse, if I redo the reverse composition, I still get the identity going on. This means that if I were to compose both ways, I have to get the identity map, because that's the only way I can get my identity matrix, meaning that T has to be an isomorphism. So, to kind of slowly wrap things up here, I want to talk about this idea of that fancier map, that cleaner map that I was talking about to go from linear transformations to matrices. So, if I have an n by n matrix, I can define what's called the left multiplication map. I'm going to call it L sub A. This goes from n-dimensional vectors to m-dimensional vectors. And the way it works is just, I take a vector as an input, the output is just multiplying it on the left by the matrix. So, very, very nice properties going on. Really, everything we have done up until this point is just shown here. So, we know that it's a linear transformation because it distributes over matrix multiplication, distributes over matrix sums, so it'll distribute over vector sums. And then scaling doesn't really matter where you scale. Clearly, if you have two left multiplication maps that are the same, the matrices have to be the same. And if the matrices are the same, you get the same map. So after that, the left multiplication map preserves sums and it preserves scaling. If I have a linear map going on, then I can say that T is equal to the left multiplication map of the matrix representation. We showed that just earlier by saying, well, if I look at the coordinate vector of an output, that's equal to the matrix representation times coordinate vector of the input. Left multiplication preserves matrix multiplication. It turns it into composition. if I were to take the left multiplication of the identity matrix, I get the identity map. And then if I have a matrix, it's invertible if and only if the left multiplication map is an isomorphism. And then the inverse of the left multiplication map would be the left multiplication map of the inverse. This is all kind of just like a rephrasing of what we've talked about in terms of a specific linear transformation. And so using all of the tools we kind of talked about, I know we'll have to like go back and prove some of the like finer details that I skipped over, but really the association between matrices and linear transformations gives us all of this. And as a final last hurrah, kind of going into a little teasing of category theory with a commutative diagram here, I can think of the left multiplication map as a map going from matrices to linear transformations. So if I have two vector spaces V and W, I'm using order bases beta and gamma because that's the ones that the diagram I have here use. If A is my matrix representation of T, then recalling that these are the standard representations of the standard representation maps going from vector spaces to like the corresponding like Fn, Fm, then if I were to first apply T and then do my standard representation, so I apply T, turn into a coordinate vector, that's the same as if I were to first turn to a coordinate vector and then multiply by my matrix representation. And we saw that before with our theorem again. Coordinate vector of a transformed vector is just matrix representation times coordinate vector. And so what I get is what we call this commutative square right here, commutative diagram. The idea behind it is if I were to start at V, run through T, then run through phi sub gamma, that's the same as if I were to start by going through phi sub beta, then running through my left multiplication map. So what this left multiplication map here does is this is really a really nice way of thinking of, okay, I can go from a matrix to a linear transformation. And that map we actually developed in the beginning is equivalent to this left multiplication map. This is just like a nicer way of thinking about it by turning it into the context of matrix multiplication. And so really, if you were to take away anything from today, it's the idea of if you need to solve something computationally, turn it into a matrix, turn it into a vector, do the computations with the matrices and the vectors to answer questions about your abstract space. And this idea of isomorphisms and matrix multiplication, this just gives us room in order to say two worlds that seem like awkward and disjoint from each other are really the same. And really, any vector space of a finite dimension can be turned into just regular vectors. Any linear transformation can be turned into a matrix. If we do stuff with our computation, then we can answer way harder problems. We can turn it into something we can actually compute. And with that, I'm done. Any final questions, comments, concerns, anything? I know I went like pretty quickly.
I just wanted to take the time to say thank you. I know that this was a little bit of a last minute rejuggling of some of the presenters, and I really appreciate you coming in and delivering again a really fantastic slide presentation for us today.
Thank you for bringing me back. I really enjoy linear transformations are just cool. And I feel like this is kind of like the coolest part of them. Ooh. Here's a question for you in the chat from Didikin. Why then study abstract vector spaces if they're the same as Fn? Stuff pops up in all sorts of different contexts. Like, if you have a context that's different than your vectors, you can turn it into a question about, like, these concrete vectors. Like, this kind of gives us, like, a computational tool to talk about abstract ideas. By using the power of abstraction, we can generalize it to a lot of different places. And if we can have this abstract idea then we can just use computational power in order to solve problems. So really the idea of like abstraction is just like being able to talk about different things in different places and really saying, oh, they're all the same idea, oh, they're all the same as this.
I wonder if like a major advantage of doing it too is just allowing computers to do a little bit of that work for us, right? Like we might be actually doing work in an abstract vector space, but if we can convert that into something that a computer can understand, like matrices and vectors, maybe that makes it a little bit easier for the computer to help us answer those questions.
I can't fully say to the computer science side of things, but I believe that's definitely, yeah, like I know with as I talked about this like last time, a lot of our like geometric transformations can be thought of as linear transformations, and so by turning them into these matrix forms, we can like have computers like do a lot of the grunt work for us and like have really just have them like represent a lot of things.
Yeah, let us know if that's somewhat helpful, Dedekind. So I'm going to close some stuff down over on Twitch.
Cool.
Oh, Zach is raiding me. Oh, well, I guess I probably shouldn't raid Zach then. In either case, I'll probably wait until that raid happens, and then we're going to shut down stream. Thanks again, Gumboy, for the presentation. I did add a little note into the Discord chat just for clarification when we were kind of talking about the derivative and integral spaces, and you were creating those kind of identity matrices.
Yeah. The 3x3 goes from degree 2 polynomials to degree 2 polynomials, and then the 4x4 goes from degree 3 to degree 3. Yeah.
Yeah, and you had brought up that really cool idea of like when you take the derivative of a, it ends up going to 0, right? So you get this really interesting thing happening in the P3 to P3 matrix where you lose that basis vector, right? Because that basis vector representing a, I guess it must be sent to, it's in the kernel, right? So that all of those vectors get sent to 0.
Yeah, your kernel of your derivative map in general is just all constant functions. So like whenever you plug in a constant function into the derivative first, you're going to get 0. So no matter like what linear transformation you apply next, you're just going to get 0. It kind of just kills it off before you can do anything with it.
So we have a question from Twitch. Can you do something wrong by self-studying linear algebra? Are there nuances and assumptions that I could miss?
I feel like that's kind of something that can happen for like anything with your self-studying. I feel like the big idea that I know from just like learning linear algebra in general and like running through classes on it, like I still like teach some of these ideas to like my high school students. I'd say like the big thing is to keep an idea of like what connections are going on whenever you're studying a different part of linear algebra, because I know really, especially in like your undergraduate like courses, like your first course in like linear algebra where it's more computational based, like the three main ideas that you've got going on, you got systems going on over here, you've got vector spaces going on over here, and then really this is related to vector spaces, but I feel like it's usually seen as its own idea, is linear transformations. Actually, let me give like a fourth thing. So linear transformations is going to be one, but then like matrices and vectors. Linear transformations. Yeah, vectors and matrices going on as like a fourth thing. So really the biggest thing I would just recommend if you're ever like self-studying it or just like learning linear algebra in general, always think back to like when you're learning something new, how does it connect to each of our contexts? Like okay, I learned something new about vector spaces. What does that say about like systems? What does that say about like vectors and matrices? What does it say about like linear transformations? Having this idea of like interconnectedness and like figuring out like one thing in a context of another. How does this help me solve something here? I think really like that's one of the biggest things I recommend, especially for like a beginning class. You'll probably like get a bunch of information thrown at you. So keeping an idea of just like, how does this help me do this? How does this help me see this in another light? Keeping those connections together is probably like one of the biggest things for just like really like any math class you take. Like, how does this thing develop the next thing, develop this previous thing from like 3 sessions ago? Just keeping these connections in mind, like really that's, and I feel like that's the big beauty of like linear algebra, like in particular, but just like math in general.
Yeah, I was gonna say just as an addition to what you just said too, that what I actually really appreciate about what we're doing here in this reading group is we actually get to chat about stuff together, right? So if you do want to self study, it's really actually helpful to self study math with a group of people that also want to self study math, so that you can bounce these ideas off of each other and discuss some of these things that come up.
Yeah, like having somebody to talk to. And like if you're ever stuck on something, or if you have an idea on something, having somebody to like bounce it off of, whether it be like a peer or just like an online group. I know like Math Stack Exchange is a really good resource as well. Just like talking through it and like reinforcing your own knowledge is helpful. I know I believe it's just generally called like the Feynman method, but I know like Richard Feynman was like notorious for using this idea. If you really want to understand something, teach it. Give the idea of like, how can you explain this to someone who doesn't fully understand it? And then once you're at that point, okay, can you go even simpler than that? And just being able to, can you properly communicate an idea?
Yeah, that, like honestly, when I taught linear algebra, that was like the first time where I was like, okay, like I actually truly understand these concepts. It's a very humbling thing to do, to get in front of people and talk about stuff that you think you know, and then you'll eventually know if you know it or not.
At the end of the day, if you're teaching it to someone who just like plain doesn't know it, like you're gonna have to figure out ways to explain it in a way that makes sense to you. And then when trying to make sense of things, that's when you're really gonna realize, okay, do I actually like have sense of it?
Yeah, because I think like one thing I always find when teaching is that I might feel like I have a good sense of something, and then a student asks me a question. I'm like, wait a second, like maybe I don't have a good sense of what's being like asked here, right?
Or you get like a question that like you didn't even like think about before. Like someone presents like a new way that you haven't even like seen, so that opens like a brand new door entirely.
Yeah, so Lally says make sure to keep an overview. Perfect. Yeah, that'd be great. Sereno, I didn't know how a vector space looked like even after my first linear algebra class. Yeah, it's true, right? You just kind of work with these things, and sometimes you don't really get the geometric flavor of what happens.
Yeah.
Cool, so I'll leave the floor open just for a few more minutes in case anyone has some final thoughts. Not seeing anything over on Discord. All right, so I think we are going to fire down stream for now. Thank you very much for the raid, Zach. Hope your stream went well, and I will catch up with you in a few minutes. Thank you, Dirac, for the follow. Welcome on into the Epsilon crew. All right, thank you again to Gumboy for the fantastic presentation this morning. We're going to sign off from Twitch, and I'll be in Discord for a little while, just kind of cleaning some stuff up. So if you need to chat with us over in Discord, feel free to do so in the simple group. Seth, raid, hi. Where would you like to raid? We could raid into high potential. I think high potential is on. Centaur, oh my god. Who made that? That's actually literally hilarious. Okay, I think I've this is like Daddy Highway all over again. Oh my god. Okay, we're gonna raid over in the high potential, everyone. I'm hoping to be back a little bit later tonight. maybe either doing some mathematics or some games. We'll find out. But I'll see you all a little bit later. So take care.
Thank you.